Go out. Okay, so basically I will read the Excel file. And in my Excel file here, I just send you one sheet, but where I store this Excel file, it has the data in sheet 2. So I write the number of sheet that has the data. So be specific. And then I extracted the information about the mean and standard deviation for the damaging flood depths and the damaging flood duration. So I have it here in column 5 and 6. So I extracted the depths and extracted the duration and also extracted the replacement cost of the component. So this is the important information that I need from this Excel sheet: depths, duration, and losses. Okay, so the next step is, do you guys remember how many steps of flood depths that I used?
1,000.
Yeah, 1001. So I have from 1 to 10 and I went to step 0.01. Here I decreased this steps because right now it will be a 3D fragility. It will be huge. So what I did, I only did 50 steps in flood depths and 50 steps of flood duration. So I made it 50-50. So, but what is the value of each step? Is it like 1 meter, 2 meter, or 0.5 meter, and the duration is like 5 hours or something? So what I did here, I want to move 50 steps from 0 to 10. So what I did, I made the flood depths vector is from 0 to 10 with 50 steps using the line space function. So line space function, basically you give it upper bound, lower bound, and the number of steps. So it gives you the numbers divided by 50 steps. Same thing with duration. I will work with duration from 0 to 300 hours, and I will make 50 steps. So if you divide 300 over 50, so you will end up with having 6 hours step. Okay, so I have here the duration vector and also the depth vector and the duration vector. If I go to D, you will find that I have 0.2, 0.4, 0.6 meters. So the step right now, it's not 0.01 anymore. It's like 20 centimeter each step. And the duration, if we check, where's EU? Yep, so here you will have almost 6 hours. Because it's not absolute 6 hours because you have a starting one. So you start from 0. So it's like you divide over like 29 or something. Sorry, 49. What was that? 300. So you are going from 0 to 300 hours. We are like saying that the flood water will stay a little bit over 10 days. Yeah, for the structural damage. So we assume that the structural damage, if the building is soaked in water for 10 days, so you are losing the structure as well, like the framing.
Can a flood do this?
Yeah, because it will be foundation, like you'll have maybe a scour in the foundation, settlement, so lots of stuff can happen in 10 days. But also it's a function in the depths. Like you will have depths and duration. So maybe you will have a very amount of depths that last for like 300 hours. It's different if you have your building 10-meter flood depths. So we capture the combination of depths and duration, and you will see it in the loss function. Okay, so right now we have our depths, we have the number of depths and the number of durations. Basically, you will find them 50, like here 50, and also the depths, you will find that we have 50 values. And the number of simulations, I reduced them to 100 so that I can run the simulation faster. So if I have in this MATLAB code, the number of simulation is 1,000, and I increased the number from 50 step to 100, this MATLAB code can take like 5 hours to finish the run. 5 hours. But when I increase to 50, 100 simulations, it takes maybe 15 minutes or so. Okay. All right, so, and here I'm selecting one component to test, like I'm selecting component number 63 to test and see what is the fragility look like for this component. Okay, the next step is to generate the samples. I have mean and standard deviation, and we have a function called normRand. NormRand, basically, if you guys remember, let's explain it again. I have function is called normRand, or log norm, rand. So these functions, what's that?
Run from random, like.
Yeah, comes from random. So these functions in MATLAB, basically, you get these functions, the mean and standard deviation, U and sigma, and it gives you simulations, random simulations, okay? Random simulations that fit this function. Like, do you guys remember we have data, like this is a reverse process for what we do in the field. Like in the field, we collect this data to get mean and standard deviation, but numerically, we need this data to generate this. So this is what these functions do. Like if we collect the data about our height and weight in this class. So we collect my height and weight and your height and weight, and we have a bunch of numbers. We have some rules to calculate the mean and some rules to calculate the standard deviation to get these. So basically, we collected these to get these. Right now, we have these to get the simulation. These what this function is doing. So right now we have three random variables. What are they? That we are studying in our depth, duration, and loss. Okay, these are the three random variables that we have the mean and standard deviation. So that's what I did here. I just initiated the failure depths and the failure duration and the replacement cost by zero vector. Why I did that? You can actually exclude this. You can delete it, but it's better because when you run MATLAB and you have already set up a matrix, he just will fill the matrix. He will not recreate the matrix. So I already have the matrix, and the size of this matrix is number of simulation multiplied by the number of component, because we have 100 simulation. That's what we asked it for. So we need 100 simulation, random simulation of the flood depths, of the damaging flood depths for each component. So basically, I don't want only one column. I need 94 column. Each column has 100 simulation for the failure depths of each one of these components. So basically, we'll have like a column like this, third column until like 1, 2, 3, until component number 94. And here you'll have 100 simulation, 2, 3, until 100. So this is the simulation, and this is the component. And this will be the size of this failure depth matrix, number of simulation multiplied by the number of components. Same thing for the duration. We will have 100 simulation for all the components. Same thing for the replacement cost. We need 100 simulation for the replacement cost of each component. So number of simulation and number of components. So generally, I'm creating a matrix that has this size. If I run this, it will have a matrix of size 100 multiplied by 94 and has all zeros. Let's fill these zeros with numbers. That's what this for loop is doing. So in this for loop, I'm going component by component to generate 100 simulation for each component. So let's attract component number 1. For component number 1, I'm asking MATLAB to generate column number 1, K1, in this matrix. Like K1 here. Can you see this K is for components, which fills this one. I need to fill the first column. These 2 points means like fill the all columns. Like if I put these 2 points, I mean from 1 to 100. Fill this with the 100 simulation that I'm gonna generate. Okay. So, but if like you want to be specific about what like 2 or 5 simulations, so you will put maybe I need simulation number 5 be equal to a random number here. So you only generate 1 simulation. But once I put these dots, I'm asking here develop normally distributed simulation with a number of simulation equal to 100, and put this 100 here in column number 1 in this entire column. Okay, and I'm doing the same. I'm actually taking the absolute because there's no duration that can be in negative. Same thing with the flood depths. I'm also taking the absolute, and same thing with the replacement cost. I'm taking the absolute so that I do not want to generate negative value for the replacement cost because there is nothing that costs -$5 or -$100. So I'm taking absolute of all the simulations that I'm developing. And I do the same thing for the duration, the replacement cost, and also the failure depths. So right now, I generated the random simulation for depths, duration, and loss. Let's see what next. The next is I'm just want to check for the test component how it looks like. So once you run this code, let's check figure 1. You will find that you have something like this. So this shows you how the distribution of component number 63 for cost. Actually, this is cost, not if you want to check something else, like you can replace this with the failure duration. I can take this Control C and I can replace that Control V, and let's separate this and run this section. So right now you will have different simulation. If you want to try different component, you can put component number 1 and check how this look like. You can put component number 2. This will show you how is the normal distribution look like for this component. Okay, so let's next do this is the big thing here. So right now I want to investigate what is the damage that can happen for each component at each flood depth for each for each flood duration for each simulation. So it's a 4 nested loops. So right now I want to test, like let's make the depth as constant. Like at depth 1 meter, I need to check if the TV at flood depth 1 meter and flood duration 6 hours is damaged or not for simulation number 1. And do it for simulation 2, 3 until 100. Then for the same depths, duration value 12 hours, and then you run the 100 simulation, 18 hours, 24 hours. Once you are done until 300 hour, then you bid the next steps, like 1.5 meter, and then keep the check. So that's what I'm going to do right now. For each simulation number 1, for each flood depths, for each flood duration, for each component, it check if the damaging DJ, let's see what is J. So let's see what is the DJ. Because I need, oh yeah, the DJ is the depth. Okay, yeah. So here I'm checking, I saw like I'm comparing the depths and the duration at the same time, but actually I'm checking both. If the damaging depths exceeded the resistance, okay, so the damaging, this part is the resistance. It's the failure depth, okay? This is the resistance and this is the resistance. This RE means resistance. Resistance, failure, duration, and also resistance, failure depth. So I'm checking. This is the actual flood depth. That's what we need to like no confusion. So this is the real flood depth. Like this building is getting 1 meter depth, but the resistance of the component is 1.5 meter. So this is 1.5. This is 1. So the component is not damaged. Okay. So this is the actual depths that we said. Like we have from 1 to 10 meter, 50 steps. So right now I'm checking, from 0 to 10 meter. And we have 50 steps. Right now, I'm checking step number 1, maybe 0. And then the next one, maybe 0.2 meter. So this is the actual flood depth. And I'm checking if the actual flood depth is more than the resistance flood depth for the component. Same thing. The actual duration of the hazard is more than the resistance duration of the components. If both happen, so right now our component is failed. Okay, so for example, so you are saying that if the flood depths happen, but the duration is not met, so the component is not failed. This is our assumption. So for example, if we have a water here, 1 feet, and stay for an hour, okay, so the component is not damaged because the flood depth, maybe this is when we touch with water, we consider the wood element is much more susceptible or vulnerable to water more than the metal. Okay, the metal can stay in the water, but the wood can like get damaged first. So you will have to met depth here and some duration. You will have to met both. If one of them met, but the other one is not met, so it's not damaged. However, you can say, but we can consider it like it's partially damaged. Like maybe it needs some repairs. We didn't consider that. It will be more complicated than us, but you can do that. We'll need one more function that can capture how this partial damage can happen. But we consider these two criteria, the damaging depth and the damaging duration need to be met. Okay, if they are met together, so right now we put one that the component is failed. Okay, and we keep doing that for the 94 components. Once we are done with the all components, we go to the next duration, like 6 hours, 12 hours, 18 hours. Until we are done with all the durations, we go to the depths. Then we do the 0.2, 0.4, 0.6 until 10 meter. And then we go to the next simulation. Simulation number 1, 2, 3. So it's 4 loops inside each other.
Do we have like 100 simulations? Duration and 100.
No, this is the simulations of the resistance. So we have a 100 simulations. So here the number of simulations of the resistance, not the actual flood depths. Like I mean, like the hazard itself. So we need to separate the resistance from the hazard. Okay, so the resistance, we have 100 simulation of the resistance. Like for example, this has a resistance 100 simulation. Like this is like 1 meter, has 1.1, 0.99, 0.89. So it has like random numbers. But the flood depth doesn't have simulation, it has values. So we need to build a curve. So it has values from 0 to 10. And these values are 0, 0.2, 0.4, and we are testing them. So the hazard has steps, but the resistance has simulations. Are you still confused or you got all of it? Okay, so this simulations, if you go back, is the one that is generated in the failure. These depths is the hazard. So right now we have a building that is exposed to a specific flood depth. So this building has a resistance, but we don't know the resistance. It's random variable. So we generated 1,000. Like we will say that this building is gonna fail at 100 tons. So we're gonna make 100 ton and a mean 15 ton. So we generated 1,000 simulations. Some of them are 115 or 150, and some of them are 89, 85. So these are simulations, random numbers. But the hazard is not probabilistic, it's a deterministic. So we are saying that the hazard are exactly 1 meter flood depths or 2 meter flood depths. Let's see what will happen. Okay, so that's what so the hazard doesn't have simulation. However, there's other research that can include uncertainties in the hazard. Like you have the flood depths, 2 meter with uncertainty 0.5 meter. So it will be much more complicated. Okay. All right, so right now I end up with having a matrix for the DM. I represent the number of simulation, J represent the number of flood depths, L represent the duration, K represent components. This is actually the core metrics for the whole analysis that we will get the fragilities, the losses, and everything. So let's get to the next. The next thing that I want to develop is fragility function for the component. If you guys remember, the first thing that we use this metrics for is to get components fragility. And the components fragility is a curve that tells you what is the probability of failure or exceedance. You guys remember when we deal with component, we look at exceedance probability or failure probability of the component, right? Because it's only one curve that tells you what is the probability of failure of the component. Exceedance is for the entire building because it's exceedance of a damaged state, not a failure of a component. And the exceedance of a damaged state is coming from the failures of a bunch of components. Okay. All right, but right now we don't have a a fragility curve. We need a surface, right? We need a surface that can tells us what is the probability of failure of a component at a specific flood depth and a specific flood duration. Like at flood depth 1 meter and flood duration 6 hours. What is the failure probability? That's what we do here. So we go from component 1 to component number n for each depth, for each duration, and here I have a counter that tells me the number of fails. And I start with 0 and keep increasing the counters as the number of simulation that fails increases. So for simulation number 1, I go check if dm is more than 0. More than 0, that means it's 1 because it's 0, 1. So if it's more than 0 and it's equal 1, so I have the number of fails will be increased by 1. So this component increase and keep trying simulation number 2, 3, 4 until I finish 100 simulation of each component. So the 100 simulation here, and once I'm done, I come here and calculate the probability of failure of the component. But right now, the probability of failure of the components is a 3D matrix, not 4D matrix. Why? Okay, so I have here the damaging, the components damage is a function of 4 variables. Okay, the first variable is the simulation. The second variable is the flood depth, flood duration, and the number of components. What I did here, I'm trying to get the components failure probability. So I test like for each component, for each flood depth, for each duration, I run over the 100 simulation, calculated the probability of failure. And right now the probability of failure is a matrix in JLK, not three matrix. Why it's a 3D matrix, not 4D matrix?
Aggregating the simulations.
Aggregating the 100 simulations. So because from the 100 simulations, I check which is failed and which is not. So I like converted this 100 simulation into one number, which is the probability of failure. So right now I have the probability of failure of each component at each flood depths for each duration for each component, F over the number of simulation. Okay. All right. So let's get to the next. Yeah, here figure 2. Throw the surface, the failure probability surface of the component. So if I run this section, let's run it. It will be something like this. So for this components, it shows you. Read it. Yeah. So here for this one, what is this axis? Is that the flood depth or flood duration? Duration from 0 to 300, and the flood depth from 0 to 10, and here is the failure probability from 0 to 1. It tells you if you have a flood depth of 2 meters, and whatever the flood duration, you have 0 probability of damage for this component. And I assume it's a second story. So when you hit the second story, you start to have fails because it's component number 63. I believe it wasn't the second story. Right now, we start to have fails. Once the duration exceeded maybe 65 hours and the flood depth exceeded like 3 meters or something, you have 100% failure of the component. Okay, so this is the surface. If you want, you can change it for other component. And to draw this surface, you basically use a function. It's called surf. Surf basically take the probability of failure. It's a 3D, right? We agreed that this function is 3D. It has depths and x-axis, y and y-axis, and it has. I put it only one number because I want to capture only one component. So I put component number 66. Like you can actually put component number 5, and I can replot this curve. Look how this curve look like. It's almost at the 0. If you put component number 10 to check this component, it will be something like this. That means, look at this. Is this component duration sensitive or depth sensitive? Depth. Why? Because at each section, like here, it's only variable in the depth. It doesn't have any variable in the flood duration. So it's only based on one. So that means like if it get touched with water, it will, like the duration doesn't have any effect. But if there is like 12 hours duration that can be damaged, or there is a range, so right now you will find the other vectors try to contribute. Let's test other components and see how they look like. Let's see component number. Okay, let's pick from here and try a component that has maybe from 12 to 16, component number 19. And rerun this section. Well, it's still not. Let's try. Okay, let's try structural components that has a very high range. Okay, let's component number 60. Well, maybe the numbers are different, but let's try 65. Yeah, here you start to see some like contribution from the flood depths and flood duration. So this is how you can know which component is duration sensitive or depth sensitive, but it also depends on, because sometimes you will not notice like it goes like very light, or it just like have a very the slope is very high. Depends on the standard deviation, and also depends on the range that you have. Okay, let's go to here. Yeah, so can you see here? It has a little bit of a range, but sometimes this can be like, it takes maybe like here from, it takes like from 4 to the depth, it's taking like from 4 to 5, and then it hits the 100. Here the duration, it takes it from like 0 until like 24 hours. Okay, so that means like this component has a range of from 0 to 24 hours to get in. Okay, so if this range increase, like let's assume that components has like a component has like 2 days to get damaged, so this curve will be much more mild. It will take from 0 hours to 48 hours. Okay. Yep, and you can actually, if you want to look, you can actually rotate this and see how's this surface look like. Is that a raw fragility or a fitted fragility? Just think a little bit. Fitted or raw? Raw fragility. Why? Because we didn't fit them. We just captured the failure as it is. We didn't use any function to fit this to a log normal. Okay, let's see. Yeah, it looks so, but actually, if you recall from last time, we have some curves that fit very well with the log normal. Some other curve doesn't fit. So sometimes the nature of the raw data looks fitted, but they are not. They need like a function that can fit them. Fitting 3D function is very, very difficult, but it can be done because you will have to fit in this direction and this direction, and it takes simulations. Like you will have to fit in X and fit in Y. Right. So, okay, so right now we are done with the components fragility. Let's see how we can develop the building fragilities. Same thing. I want to get the exceedance probability of damage state 0, 1, 2, 3 for each flood depth and each flood duration. I have a groups of components, and I'm checking based on, I'm weighting their damage. You guys remember we weighted the damage from, if you have 4 fragility curves or 4 fragility surfaces, component that has value $5,000, component has a value $1,000. So sum all the components in each damage state. For example, it will be 100K. Some of them has a value of 10K, so it will be 10 over 100. So the contribution of this component will be 10%. But some component has 50K, so the contribution of this component will be 50%. But the contribution of all the components shouldn't exceed 100%. That's what the weighting is doing. So that's what we did. So we are checking for damage state 1 component from 1 to 6 based on what we have here. Sorry, actually I'm looking on another Excel sheet, but actually it's the same concept. This is the one from your homework. Because yeah, so that's a good, the one from your homework, I gave you another archetype, archetype 1. The one that I'm doing here is a 2-story residential building. The archetype that you will do for your homework is a 1-story residential building. which explains why the number of components here are 64. The one that we used is archetype number 3, which is this one, the one that has 95. Yeah, so I have this group of components. These from 1 to 6 are damage state 0, and I have from 7 to 13 damage state 1. So here in my code, I'm checking component from 1 to 6 and trying to convert them from 6 fragility surfaces to only 1 fragility surfaces by weighting them by the replacement cost. This is the weighting function. Doing the same thing for damage state 1, 2, 3, up to damage state 4. Then here I'm trying to, since I have damage state 0 as a 1 matrix and damage state 1 as a 1 matrix, I'm trying to put all of them in a 3D matrix. So that's what this matrix is doing. So damage state 0, if you guys remember from the last time, it was 1 vector. It tells you what is the failure probability of what is the failure probability of the component at specific plot X. But right now, damage state 0 is a 2D matrix because it has on the x-axis duration and the on the x-axis depths and the y-axis duration, and tells you what is the failure probability at this depth and this duration, this depth and this duration. So it's something like this. Like here, depth, and this way, here's duration. And here is the failure probability. So for example, if I open damage state 0, so we'll find 2D matrix, these numbers. In the last exercise from last lecture, we only have 1 vector at 1 duration, assuming like, for example, it is a 300 duration, a 300 hours duration, like the maximum duration of the camp. It's only 1 vector, but right now I have a bunch of vectors. Like you can imagine this as you have 100 fragility curves that builds a surface. Each one of these is a fragility curve. Once you sum all of them together, they will make a surface. Like you have a one duration, 6 hours, 12 hours, 20 hours, and then you like connect them to make a surface. Okay. So, and what I did here, I just put all the damage state in one 3D function, like this ds, it will be 3D function. I have this one layer of the 3D function that has damage state 0. And I can make another layer for damage state 1, and another layer for damage state 2, another layer for damage state 3, and so on for damage state 4. Then I convert this to a 3D matrix. You can do this step or not, whatever you like. So here in figure number 3, let's see what we have in figure number 3. It's a subplots. I plotted the damage state in 1 figures. Okay, so this is how it looked like. Okay, so this is damage state 0. I believe this is 1, 2, 3, and 4. I didn't plot 0. 1, 2, 3, 4. Is that raw damage states or fitted damage states? We are still raw damage state. We didn't do anything. Can you see how these fragilities look like? It's not fitted. This one look, but the thing is, because it's damage state 4 that has the structural components. So the structural components are highly variable in the duration. So right now you can see the contribution from both. But this, most of them are electronics, appliances, furniture. So the contribution of the duration is not that high. Okay, so this is how the fragility surfaces look like. As a feature of the 3D surfaces, you can, I believe for each one, I'm not sure if you can rotate or, oh yeah, here. You can rotate this one and see how it look like. So this is, shows you how the surface look like. Similarly here, you can see how the surface look like. So this is damage state 1, 2, 3, and 4. Figure 30. Oh yeah, I'm plotting them alone, like damage state 0 alone. So if you want to visualize them alone, you will find them by themselves here. for each one. Let's see what is next. Figure number 35. Oh yeah, so here I'm plotting them at the same figure, like all the 4 damage states. Can you see how they look like? If we visualize them from the side, you will feel that they exactly look like the 1D damage state. If we looked at them like this, you guys remember from the paper. Okay, so this is the fragility functions for this archetype. This is the 2D only function in depth. Look at this curve, 35. These 3 is this 3, and this one is this one. This is the raw fragility, not the fitted. This one is the fitted. This looks like the raw. If you guys remember how the shape look like, will be exactly like the raw fragility. But what we did in this one, we captured the whole thing, like how it's looked like with time. But I have a question. What section of these, like if I take a section 180 hour, it will not match the raw fragility that I have for the 2D function. Why it's like at 300 hours, it matched what I have from previous time? What was that? At the 300, because the approach that I used to develop the 2D fragility, I assume that any component that get touched with water will be damaged, whatever the duration is. That means like assuming that each component reaches the maximum flood depth. Here in the developing in this, the maximum flood depth was 300. If all the components are subjected to 300 hours, all of them will be damaged. So at 300 hours will represent the 3D fragility. And I want to show you actually when I take sections and this surfaces, how they will look like over time. Actually, I have a publication that has the okay, so it's applications. Yeah, disaster risk reduction. Published papers. This one. Yeah, so here, this one. Can you see this figure? This I take a section in a 3D surface fragilities and shows you how the fragilities look like over the time. So if you cut the fragility surface at like flood duration 1 day, you don't even have damage state 4 because the building will not reach damage state 4. To reach damage state 4, you need a structural damage. 1 day, it's not enough for the flooding to make structural damage. I mean, like for the system, the foundation, the walling, the framing, the roof. So you have damage state 1, 2, 3. Same thing until damage 2 days. Can you see how is the yellows going up? And then the damage state 4 start to show up with days until it gets more, and it gets more with the number of days. So this is when we cut at different sections of the flood fragilities, how they look like. Actually, it takes maybe hundreds of lines of code actually to do this cuts in this figure. I'm not kidding. It will like coding to just plot some sections in this 3D. So, okay, let's get back here. Yeah, all right. So the next step is the fitting. So here I'm doing fitting for this. I'm doing log normal fitting for this 3D surface. So what I'm doing here, I'm using the same fitting function, but I'm doing a fitting for the flood depths using for loops and fitting for the flat duration using another for loop. So once I'm done with the depths, I did the fitting for the duration. This is only one round. You can do a second fit. I believe I did a second fit. No, it's just like versed fit. So sometimes like the fitting, you don't like it. Like, okay, it's not fitted yet. So let me do another round of fitting. So maybe after the second fit it will be good, but I was satisfied with the fitting from the first round. Then here I was, okay. So for the fitting, basically, if you guys remember from the last time, how's the fitting function work? You basically give this function. If we are fitting the depths, we are giving it the raw depths and the raw value of the exceedance probability of the damage states, the raw values, not the fitted values. And it gives you back different depths with different exceedance probabilities, because you have, so you give this, you have a function like this. Something, this is the raw one, okay? So each plot depth like this, each flood depth has a specific value for the exceedance probability. The fitted function will be something like this, okay? So right now it will give you different flood depths, not at the same flood depths. It will give you a bunch of flood depths fitted, like values for this curve, right? So this is what this function is doing. It will give you depths, ds, and CDF for the log normal function. We do the same thing for the flood duration. So you will have durations. Right now I'm trying to plot the CDF. So let's see plot number 311. Look at these functions, how they are different. Like this one is damage state 1, I believe. So looks different from the other one. This is how is the fitted one look like. However, it is not that fitted perfectly. Can you see this? This one? It needs another round of fits so that you can expose this part. Okay. So
You fit each curve alone.
yeah, you fit each curve alone. Like you actually, each one of these lines is a curve. I'm fitting them this one by one. Okay, but the thing is, you are fitting in X and you are fitting in Y. Sometimes you will not match. There's different approaches for fitting. I believe we use the basic approach when we did this fitting, but there's other advanced approach. Like you have a function of surface that has parameters and you keep playing with this parameters. Okay? Like a function that's alpha and beta and gamma, and you keep trying to fit a curve with the best values of these parameters. Okay? I believe there is a fitting toolbox in MATLAB. It's a very big toolbox with lots of functions. You can try them if you want. Okay, so here, okay, I have it. Yeah, I plotted damage state 1, 2, 3, and 4, and I think I have a plot that combine all of them. Yeah, I plotted them in one plot in 3, 6, 1. Here. So all of them are here. If we rotate this curve, yeah, look at this. Now they look much better. Can you see? However, in the fitting, you can see that two of them are intersecting down here. This one has some values here, but that means like damage state 4 is more than damage state 3. So you can exceed damage state 4 before exceeding damage state 3. But this sometimes happens when we do fitting. And if that happens, that means like we neglect damage state 3 at this region because damage state 4 has been already exceeded. There is a publication that talks more about this, but this is just like a brief explanation. And how's this fragility look like? And I believe the one that I presented in the paper are the fitted one, this one. Can you see how they look like? Yeah, all right, so let's get back here. Yeah, so right now we are doing only fragility. We didn't do losses, okay? So let's see how we calculated losses. If you guys remember, last time we have an approach that we said, rather than converting from component fragility to component loss and multiplying the failure probability of the component by the replacement cost of the component and getting component loss, there is a way that we can get component loss directly. Like if we have 100 simulations, it's the same thing. Okay. Rather than saying 100 simulations are giving us a probability of failure and then multiply this probability of failure by the replacement cost, we will use this 100 simulation to get the replacement cost directly. If a component fails, so you lose all the value. If the component doesn't fail, so you will keep all the value. Do this 100 simulations and get a mean and standard deviation will give you the same thing. So that's what we did here. For each flood depth, for each duration, each simulation, each component. If the component is damaged, like damage more than 0 means 1. So the component loss is randomly calculated from the mean and standard deviation. Okay, so we pick a random selected replacement cost. Okay, so it is the same, has like the same meaning, but it will give you like same calculation. And we don't pick, like we say, if a component got failed, we say that the value is not an exact value. Pick a random value using this mean and standard deviation. So it will be picked randomly. And we do this 100 simulation. Like here, pick a random value like norm rand from the mean replacement cost and the standard deviation of the component. Once we are done with this, we get the mean component loss. So let's, for example, can we imagine? We did 100 simulation. Out of this 100 simulation of the component, 80 simulations failed. 80 simulations failed. So this 80 simulations have a randomly selected value of the replacement cost of the component. Okay, we take this 80 and take their mean. So we have their mean here. So you get the mean component loss by taking the mean of this one. So right now, which one that we are taking the mean? Like we have J, L, I, K. So what we are taking the mean? We are taking the mean of the 100 simulation of the replacement cost. And the simulation is I here, number I. So we are taking the mean of column number 3. And we are taking the standard deviation of column number 3. So we converted the 4D function into 3D function by taking the mean of the simulation. And right now we are trying to convert it to 2D by only focusing on one component, like by selecting only one component, like K1 or K2 or K3. So if you look here, you will find that I have a component here. I got the mean replacement cost of this specific component, and I try to plot the loss at figure number 4. Let's see what we have in figure 4. Is not here. Okay, let's run this section. Okay, it's something like this. Can you see how it looks like? This is how's the mean replacement cost of the component look like. If you increase the numbers of simulation, you will have a much better surface. Like this surface will look like this. Actually, when we published this paper, like the reviewer asked us to show us how's the random values look like, how your points look like, because the surface is so on, why you didn't increase. We did 100. He asked us to do 1,000, and this was why we moved it from 100 to 1,000. Actually, let me show you to get some experience. Blood actually was in 2020. Yeah, this one. Author responses to the reviewer. Yeah, okay. So actually sometimes the author responses to a reviewer can be too much, but this was the second review, so it wasn't that much. So let me show, it was 18 page, like to respond to a reviewer. More than the paper.
Oh my God. How long was it?
Yeah. Yeah, so he was asking why you didn't use a 1,000 simulation. So this is the difference between 100 simulation for 2D curves. Can you see? It's not that smooth, right? When we use the 1,000, we start to have a smooth fragility curve. This is how's the simulation if you are using 100. And we did the same thing here. This is if you have 100 simulation. And this is if you have 1,000 simulation. This comes like, this is how the samples look like. Can you see how the scatter of the points look like? And this how's the smoothing of this point. How you pull a surface that can't represent these points. So, and this is if you look at the 2D. You guys remember when we have a 2D, we have like similar scatter like this from last time. This is how the points look like. Okay, so let's get back and finish this. I'm done right now with the component replacement cost. The next step, let's escape this non-run, is to calculate the total building loss. And if you guys remember from the total building loss, basically here, this component loss, you have the component K. It's a 4D function, right? Number of components is the vector number 4. So I want to sum all the losses from all the components. So I compress this 4D matrix into 3D matrix by summing the value of loss for all the components which are vector 4. So, and that's actually what I did here. So I take the sum of component number 4 and then I reshape, I take the mean of mean total building loss. Okay, and then I took the mean of all the simulations because I have 100 simulation. So let me show you back. The 4D matrix, when I compress it to 3D, it will give me this points. Okay, this one. But right now, I want to get the mean of all these points. So I want to take the average of the 100 simulations that I have. So I take the mean. If you guys remember, the number of simulation is vector number 3, I. So I take the mean of I. Number 3, we take the mean and standard deviation, and then I plot the mean total building loss. I serve all the means. So if you look at figure number 5, here, it will be something like this. Right now, I have the flood duration here up to 240 hours or 300 hours, and from 0 to 8 meter flood depths, or whatever, like 10 meter flood depths. Then I plot the total building replacement cost of each one, each flood duration and each flood depth. And this is coming from 100 simulation for the 94 components. So I have a 4D matrix, depth, duration, simulation, and components. First, I compress all the components to get the building and take the mean of the simulations. Then I moved it from 4D matrix to 2D matrix, function in flood depth and flood duration. And for each flood depth and each flood duration, I have the total building loss. And this is the function that I did. What I did here, I plotted the 2D functions that I have over the 3D functions. This is how the 2D function look like. It captured the losses maybe at 140 or 150 hours. It matched this. The red one is the hazardous stage damage. So hazardous stage damage functions shows that it represents the loss of the surface that matched duration by 60 hours, which also can represent how hazardous assumed the losses. Maybe say assume like that the water is not gonna stay for like 60 hours, or the samples that they picked was water that didn't stay for more than 60 hours. So there's lots of things that we can validate this. So here's a choice. How is the function representing the 3D as over the 2D function? All right, so I believe this is the end of the whole thing here, where I was plotting the 2D curve on a 3D curve. It's a little bit tricky to plot 2D curve on a 3D surface. So here's, it shows you how to plot it. And I believe other than that was like some extra work that is not needed. So I like excluded it from the analysis. Does anyone of you have any question? It's a little bit difficult. I'm trying like to give you an overview. Maybe you need that in your research. Maybe for wind, maybe you want to capture the wind velocity with something else. So who knows? Like if you want to do it, so there's a ways to do it. If you have any question, email me or send me a message. I'm gonna assign a homework for this one. It's basically like the homework that you have, you'll just add more codes. You can copy paste and add the duration, okay? Just like to have a feeling of how 3D surfaces look like. These things is very, very important. If you have very good experience with developing this stuff, you will be in a different place. Just try to practice and you will be great. All right, okay. That's all for now. I'll see you guys next time.
Thank you.